session is the modal decomposition methods for aerodynamic flows. Your session chairs for this session will be myself, Doug Smith. I'm with the Office of Naval Research, and Professor Sam Tyra from Florida State University. So this is an invited session that was organized by the Fluid Dynamics Technical Committee. And I'm pleased to state that we have 7 distinguished experts here who will be discussing modal decomposition methods. They will be presenting overviews of 6 of these decomposition methods. And as you may have noticed from some of the people standing around the room, we're going to be video recording this session. AIAA has graciously agreed to record the session and provide the video up on its YouTube channel, as well as providing the video recording to the Fluid Dynamics Technical Committee for future use. I'd also like to thank the speakers today for graciously agreeing to allow us to video record this session. It's nice to know that we're going to have an enduring product from this session. So if there's something you see today that was particularly interesting, you should know that you'll be able to go back and review that in the future on the YouTube session. So we have 6 talks on decomposition methods, but before that we're going to have an introduction by Tim Colonius, who will set the stage for the presentations that are going to follow after that. So we're going to start off. Tim's going to give us this overview. Tim is a professor of mechanical engineering at Caltech. He has a bachelor's degree in engineering from Michigan and a PhD from Stanford University. So with that, Professor Tim Colonius, thank you.
Okay, well, thank you, Doug, and thanks to both Doug and Sam for inviting me to be here today to tell you about this discussion group that's been going on the topic of modal decomposition. So, in a nutshell, the working group has been struggling with this sort of stew of different acronyms for decomposing flow fields, and trying to basically answer the broad question, what are these things, and in the context of practical aerodynamic and other types of flows, what are they good for? So my sort of challenging task for this first talk is to try to sort of set the stage to tell you a little bit generally about what modal decompositions are, and try to lay out a sort of a framework that I hope will be helpful in the talks that follow me. So the background here is coherent structures. Whether we're dealing with transitional flows or turbulent flows, we all have seen a variety of these structures, both in natural flows, engineering flows, and really this is a topic that's not limited to fluid mechanics. It's very much related to structural mechanics and really all of science and engineering. So, let's take apart the term coherent structure. So the noun here, structure, a common arrangement of elements or a pattern. Why are we interested in patterns in flow fields? Well, the concept of a structure is a natural one in trying to reduce the complexity of something. We describe a whole complicated structure as one unit rather than many of them. And coherence implies that this structure is sticking together, lasting. And then if some structure is recurring in a flow field, is lasting in a flow field, then we would imply that has something to do with it, that it's somehow important for the dynamics of the flow. So, in terms of modal decompositions, why is that a useful way to think about coherent structures? Well, the modal decomposition is the mathematics, the machinery, the algorithms where we can actually find these structures from data. And particularly when we're dealing with large volumes of data from particle image velocimetry or CFD, we need techniques that can take these large data sets and extract structures from them. And moreover, we want to think about different kinds of decompositions to have the sort of most objective or useful definition of a structure. You know, we all see a structure and we might see different things about it, but when we try to define that structure mathematically, we have to be objective in that definition. So these modal decompositions also help us understand how these structures occur. Why is it that the governing equations of fluid mechanics prefer to organize the flow into these structures? Are there underlying instabilities or amplification processes, for example, that create these structures? And finally, we want to exploit the structures. So one simple thing we can do if we understand the structure in the flow field is compress large data sets. But we can also use the structures to give us ideas about reduced order models for the flow field. And perhaps most importantly, they provide handles for control. If we understand how to attenuate or amplify these structures, we can achieve interesting things in flows. So I apologize in advance. I have a lot of math on these slides and not a lot of time to go through it, but this is a sort of a mathematical topic. So what I wanted to do first is lay out a sort of conceptual flow model, and I don't want to get caught up in writing the Navier-Stokes equations, equations of energy, all the things we might need to describe a compressible or an incompressible flow field, but just kind of give you the conceptual version. And to do so, I find it useful to think about a flow field that's already been discretized. So we're going to imagine that we're doing some kind of a CFD of the governing equations, and we are going to write a discretized set of equations. And the variable Q here is going to be all of our flow states, all of our flow variables at all different grid points. Say if we're using a finite difference scheme, we can just think of these as the nodal values of these velocity and pressure and so on at the grid points. If we're using another kind of method, then these are different kinds of discrete modal values, but we can just think about them as grid points for the point of view of this talk. So the governing equations are basically simple in this form. We have the time rate of change of the flow variables is given by a quadratic nonlinear term. So this is the advection in the Navier-Stokes equations, plus a linear term, typically just a linear diffusion term. And then because we've discretized the equations, we have here a sort of an input term. So these inputs could represent different things, either in an experiment or in a flow simulation. They might represent some kind of a forcing of the flow field. Oftentimes in doing DNS and LES, we have to excite the turbulence somehow. We have to add a volume force somewhere and tickle the flow to excite the turbulence. So that would reside in this input term here, as well as things that come from, for example, inhomogeneous boundary conditions, which in the discrete world would be written as a term in the equations like this. We have an initial condition to this system, which typically we wouldn't know, but we can sort of formally write it down. And then we have a set of observables, which I'm going to call Y. And the observables are related in some way. Here I'm just assuming linear, but this could be more general as well, a function of the flow state. So in many of the decompositions we're going to be interested in, we really only have this output data. We have observations at a limited set of points in space and time. So the framework can be written fairly generally for the decompositions if I first perform a sort of Reynolds decomposition of the flow field. So here I'm going to take a flow field and I'm going to decompose it into a base flow plus some perturbations. And the base flow can have different meaning. It will have different meaning in different parts of this talk. So Q bar could represent a laminar equilibrium solution, some solution of these equations where dq bar dt is 0. It could also be the mean of a turbulent flow, in which case we would have the mean flow would satisfy the sort of Rand's equations written here. So they would involve the mean of the products of the fluctuating quantities. But in either case, we can go through the machinery of injecting this decomposition into the equations and looking at the part for the flow perturbation. We're interested in the structures in the flow. We need to think about what happens to the perturbations to this basic state. So if we write that down, we get dq prime, the fluctuations dt, are equal to, I separated out all the linear terms in this equation into a big matrix A times q prime, and then I've grouped all the nonlinear terms into this term r prime. So these are essentially the instantaneous fluctuating Reynolds stresses. And then we have whatever inputs are acting on these perturbations. So in thinking about decompositions, the first thing that we should do is think about the symmetries of the underlying flow field. Either if we're, those symmetries arise typically because of the geometry that we're using for a particular problem. So for example, if I have flow in a, that's already dead. If we have flow in an infinite, otherwise infinite channel here, then I have two two homogeneous or periodic directions. And what that tells me is that if I observe a flow structure at any particular place in this channel, I'm just as likely to observe that same flow structure at some point further downstream or some point, another point across the span. such that the statistics of these structures have to end up being independent of these two coordinate directions, the span-wise and stream-wise directions in this particular flow. Similarly, in a round jet, I have axisymmetry of the geometry, and the Navier-Stokes equations also enjoy that symmetry. And so any structure I observe in the jet can also be rotated through any angle and be just as valid a flow structure for the jet. And then other kinds of systems have reflection symmetries. For example, this flow in a sudden expansion, I might have a structure separating from one wall. Well, I'm just as likely to have that same structure happen separating from the other wall. So in doing modal decompositions, it's almost always of benefit to take care of all these symmetries at the outset. And it's not always obvious how to do that. In the case of homogeneous directions, however it is, what we do is we do a Fourier decomposition of the flow field in whatever homogeneous or periodic directions we have. So in what follows in this talk, I'm going to assume that we've sort of taken care of these symmetries ahead of time. So if we're dealing with homogeneous directions, we've already Fourier transformed the governing equations into Fourier modes in those particular directions. And so we'll call these new kind of modal amplitudes Q hat. So we've already kind of introduced in that slide the idea of a modal decomposition, breaking up a flow field into a number of pieces, in this case, Fourier components. And now we want to think about the more general case of how do we deal with inhomogeneous or general case modal decompositions. So here I've rewritten these equations for the hatted variables, once we've accounted for the symmetries of the system. This is a good point of any to introduce what is the so-called adjoint system here. So basically in this simple notation, and this is the linear adjoint, we simply have the adjoint variables are governed by the same equations, but with this matrix transpose. This is the Hermitian transpose in the case when A hat is complex. And then it's the output matrix here, C hat, that appears in the adjoint formula. So these adjoint variables come in a good number of these decompositions. So here's the decomposition we're going to deal with. We're going to say, can I break the fluctuating flow field up into a series of modes, phi? And the phis are going to, at least in the first instance, be purely spatial modes. So they're represented by a vector of flow quantities and grid points, just like the dependent variable q. So the phi dimensions of phi are exactly the same as the state vector q. And then we multiply them by some modal coefficients, which we're going to call alpha, and we sum up over those modes to get whatever representation of the flow field we want. I'm going to put this equal to q hat r. This is going to be some reduced description of the fluctuating field based on a limited number of these modes phi. So for example, phi might be a complete basis for whatever the state space I have here. If this is dimension n, I might have n of these phi vectors in total. But we're going to sort of draw a squiggly line here and break off this set of modes at a limited number r. And I'm going to use this notation a lot of taking a bunch of different vectors and making them the columns of a matrix. And so the lowercase will be the vectors and the uppercase will be the corresponding matrix. Okay, so again, here the aim is to make r small, and the aim is for these basis vectors phi to somehow represent the important structures in the flow field, the important vectors subspace that comprises the vector q, say. So the concept of projection is very useful here. So here are a set of modes, phi1 up through phi r. I'm going to introduce a second set of basis vectors. We might call these trial vectors or test vectors. I'll call those psi. And what I'm going to do is I'm going to project my flow data onto a subspace. So in working with these finite dimensional vectors, this all boils down to doing some linear algebra. We can write down a projection matrix, basically, which is going to project any vector into a subspace that's spanned by the first r of these phi modes. So phi are going to define this space. Here's a little picture of what we're doing here. So we're going to, this is very easy to conceive of in a three-dimensional space. We have the trajectory of the flow field, which is represented by some time movement of a point in this three-dimensional space. We're going to project it onto a subspace of just two of these vectors, phi1 and phi2. So we're going to project it onto the blue plane. And we're going to take the projection in the direction of the red plane here. So we're not necessarily going to be doing orthogonal projections, but in general they can be oblique. So the psi1 and the psi2 represent this plane of the projection. So when we project our flow data q, we're going to have some representation qr. That's going to be the red curve on the blue plane. And what's important to distinguish at the outset is that we often are interested in a model for the dynamics of these first few R modes of the flow field. So we can also project the whole governing equation onto this subspace. We can project the dynamics, as it were. So here's the equation for how the modal coefficients vary in time according to a reduced model where I'm projecting onto the subspace. But the aim here would be meant to make the trajectory, the solution of the blue system here, to be exactly the same as what the natural flow would be projected in this space, so the red curve. But as it turns out, it's not always possible, and it's certainly not easy to make the blue curve exactly align with the red curve. Even for a linear system, it's certainly not the case automatically that if I project the flow data, that the dynamics will also project into that space. And in the nonlinear case, it's certainly not the case that it will, and that's what we need to worry about. So here I've tried to formulate all the different decompositions we're going to talk about in this session on a sort of a single slide. So they can all be understood as being different ways to decompose this flow model, this system of equations. And there are two different types. One is based on realizing data of this flow system, either by solving it on a computer or by doing a corresponding experiment, where maybe I never even write this flow model out, but I have in the back of my head that, yes, the flow field satisfies some conceptual set of Navier-Stokes equations. So I generate data. Most often I generate data for the outputs here, y, the observables. If I'm fortunate enough to be doing a simulation, I can actually observe the entire flow state Q. And if I'm fortunate enough to solve the adjoint equations, I can also observe the adjoint solution Z. So Y would be the thing I would typically have from experiments. I would not typically have, or I would not really ever have Q and Z. And you'll notice I've used this same formulation here. I'm taking observations, M of them all together, and I'm piling them up in vectors. This is called a data matrix. This comes up in almost all the decompositions you're going to see today. And these different vectors can represent two different things. They can represent snapshots of the flow field, so just taking individual instances of the flow field, but they can also represent realizations, different realizations of a random process, for example. And I'll try to make it clear which is which as we go along here. So data-driven decompositions tackle these data matrices, Y, Q, and Z. And whoops, I think I made a mistake here. Yes, I'm sorry. So now you need to come over here. This group goes with this block over here. Sorry about that. So the data-driven techniques we're going to talk about are POD, proper orthogonal decomposition, dynamic mode decomposition, and something called balanced POD. On the other hand, we can work, instead of with data, we can work with essentially the operators, A hat, B hat, and C hat. This is really all of the information, at least about the linear part of the dynamics, is contained in these three matrices. R hat is also important. That's all of our nonlinear effects, but these are generally not used in defining the decompositions. So when I'm dealing with the operators, or the matrices in this case, then we're talking about things like global modes, or linear stability analysis, resolvent modes, or balanced truncation. Okay, so global modes, or linear stability analysis, is one way of defining a set of structures in the flow field and a corresponding set of modes. So in linear stability analysis, we're taking the linear case, so R hat is going to be 0. Our base state is going to be a laminar equilibrium solution, possibly stable, possibly unstable. And what we're going to do is we're basically just going to write the solution of that linear system using the matrix exponential here. It's a very difficult thing to compute, but conceptually it's quite simple. We have the long time stability of the flow being governed by the eigenvalues of the matrix A. When those eigenvalues have negative, the maximum real part of the eigenvalues is negative, then all the fluctuations in the system eventually decay, the system is stable. When they're positive, then eventually the solution of the system blows up to infinity. And if they happen to be, the maximum happens to be 0, then we have the borderline or neutrally stable case. So in fact, these eigenvalues we can get by doing an eigendecomposition of the matrix A, and that's what's going to form the subspace. So the right eigenvectors of the matrix A are going to be the linear stability modes in the flow field, and the phi vector in this case is just this set of right eigenvectors of the matrix A. We can also, in this case, define a nice corresponding set of adjoint eigenvectors or left eigenvectors of the matrix A. And it's particularly useful to use those for the psi vectors in this case, the direction of the projection, because then that projection is basically one that takes us to the eigenspace of the matrix A. So it separates all of the different linear modes of the system into growing and decaying modes. So for example, if we apply this to a flat plate airfoil, as was done by Ahuja and Rowley, so this is the flow over a very low Reynolds number of 100 over a flat plate airfoil. CL over CD is plotted as a function of angle of attack here. And there's a stable steady state solution up through a particular angle of attack, after which there's an unstable steady state solution, which is given by the middle of these three dashed lines here. So what's been done is that for this unstable equilibrium solution here, the eigenvalues and eigenvectors of the matrix A have been found, and they're represented graphically over here on the slide. So the one with the highest growth rate, the most unstable mode here, is plotted, the real part and imaginary part. This is an advecting structure in the wake of this airfoil. It's very similar. It's identical, in fact, to the structure of the mode for vortex shedding over a circular cylinder. And the corresponding adjoint modes are plotted over here. So this view of linear stability is an especially simple one, and if you've been somebody that's been studying hydrodynamic stability all your life, you'd be thinking like this is a gross oversimplification of stability analysis, and it is, but the key to its use in this context of modal decompositions is that with modern computers, we're able to tackle very complex mean or base flow fields with linear stability analysis. So the term global here, which we don't really need in this context, it's used to distinguish this analysis from corresponding concepts that we use for locally parallel flow fields. In other words, we're no longer concerned just with one-dimensional eigenvalue problems as we are in classical parallel flow stability analysis, but we're interested in the corresponding 2D and 3D eigenvalue problems. The enabler for this are fast computers and good techniques for fast linear algebra. I won't talk about those things today, but this really underpins all of what we're talking about in this session. And when we have this view of this simple view of stability as comes from this perhaps huge matrix A, some things we think of instabilities as flow fields. For example, our friend the Kelvin-Helmholtz instability in a typical shear layer is no longer really an unstable mode of the flow. If the flow is spreading, that Kelvin-Helmholtz mode is actually realized in this system as a stable mode. It has a finite rate of amplification. So some of the terminology that we use from classical linear stability analysis is not so apt here. So one of the key things that has sort of taken off in the past 20, 30 years has been the idea of transient growth, or what happens when the system is actually stable. If a system is stable, does that, we know that implies that eventually all the disturbances will decay, but in fact, for many matrices A, particularly ones that have a set of eigenvectors that are nearly parallel to each other, not quite, but nearly parallel to each other, we can actually have a very large transient amplification. So disturbances can grow to quite a large amplitude, even though eventually, at least in the linear case, they would decay. So a way to analyze this is by thinking about the solution of this linear system in Laplace space, which is written here. So the outputs are now in Laplace space, y tilde, and we have the C matrix, the inverse of the dynamics of the system, SI minus A inverse. And then these are being forced either by an initial condition or by some kind of a input to the system. And so the idea of transient growth is encapsulated in this matrix. And we can ask the question, if S happens to be an eigenvalue and the flow were unstable, that would imply that this amplification is infinite. But when S is any other value than that, then we might still have a large but finite rate of amplification. And so that's typically characterized by the singular values of this matrix, the largest of which is essentially the 2 norm or amplifying power of this matrix. So this is the so-called pseudospectrum, one version of which is taken from Trefethen's website, is plotted here. This is the imaginary S and real S. We basically plot contours of the largest singular value of this. The little dots here represent the singularities. Those are the points where this is actually infinite. And the lines here represent finite rates of amplification. And particularly what's interesting is to look at this along the imaginary S-axis, which corresponds to a real time frequency. And that real time frequency characterizing the system here is a concept called the resolvent. So when we write this along the imaginary S-axis here, I've simplified it here, y of omega. We call this the resolvent operator. And this is interesting because it tells us in a sort of steady state fashion or stationary fashion, how is it that inputs are amplified into outputs of the system. It's basically a transfer function, but a multidimensional one. Okay, so resolvent modes are the next set of basis modes we're going to worry about. And they're basically going to be found by taking a singular value decomposition of the matrix R. This is how I would find that largest singular value that would represent the gain, but I can in fact get a whole matrix of gain. I can decompose the whole R into a set of orthogonal output vectors U and a set of orthogonal input vectors V that are related by a set of gains sigma. So these are quite interesting because the largest one, if it's separated in value from the other ones, represents a sort of a low rank, high gain thing happening in the flow field. And in particular, this has been particularly interesting for analyzing turbulent flows. And this is one of the points I really want to hit on here is how this resolvent process helps clarify how we get large-scale structures in turbulent flows. So in this case, the base flow is going to be the mean of a turbulent flow, and I can worry about two kinds of inputs. I can worry about generic sort of stochastic forcing giving rise to turbulent structure, but I can also worry about how the turbulence itself, how the sort of chaotic and nonlinear triadic interactions in the turbulence lead to, through this linear amplification, large coherent structures that I might actually observe in the flow field. This is just an example of that. I think I'm running very low on time, so I'm going to have to zoom through this quickly. This is a calculation that Oliver Schmidt and I did recently of a fully turbulent, very high Reynolds number jet. The corresponding flow simulation is from a large eddy simulation. And we've taken the mean flow field from that large eddy simulation, and we've basically computed this resolvent operator directly and decomposed it via the SVD. So this is a plot of the gain as a function of the real frequency in the jet cast as a Struhal number, and the optimal mode here, the sigma 1, that's the highest gain mode. You see here has this spectrum to it, right? So there's some particular frequency. This is called the so-called preferred frequency of the jet where I get the maximum amplification. When I look at this at a different frequency, I'm not going to look at the peak here for reasons that I'm not going to share at the moment, but I'm going to look just off the peak over here. And what I see is an input mode that's dominated very near the nozzle exit. So somehow the turbulence is exciting this mode of the jet very near the nozzle exit, and that thing is growing into an extensive wave packet, a very large wave packet in the jet. And interestingly, this prediction, according to this resolvent analysis, agrees very, very nicely with what we actually observe in this flow field using POD, which is a technique that I'm going to describe next. So this is, so we have this sort of resolvent analysis and global stability that are tackling the operators in this flow problem. When I attack the data directly, I have things like POD and other techniques. So let's just consider POD for the moment. So I'm going to realize, in this case, the flow state. I can also realize the observables. I'll say more about that in a moment. And I'm just going to observe it m times and create this data matrix. So what POD does is it takes the covariance or cross correlation between each and every one of those different observations, so every point in the flow field to every other point in the flow field, and it decomposes that matrix into its eigenvectors and eigenvalues. All right? So the eigenvectors, because this matrix C is Hermitian positive definite, these eigenvectors are actually now an orthonormal set of vectors, which is very useful. And so the phi define these so-called POD modes of the flow. The simplest way to interpret POD is with, again, a simple two-dimensional example. If I just have two flow states, Q1 and Q2, and I observe it a whole bunch of times here, right, what POD does is it tells me how to rotate the coordinate system here such that the first direction, the phi1, is in the direction of most of the variance or variation in the flow data. And then phi 2 will be in the direction of the next most variance, and phi 3 the next most variance, and so on. So in this cooked up example, almost all the variance is in one direction, so this data would be very well described by a single POD mode, for example. Okay, I've written everything here in terms of finite dimensional vectors. There are extensions to everything I've told you about to a finite dimensional Hilbert space that we could use if we're dealing with continuous variables. One important thing I need to tell you is I've skimmed over how we define the sort of norm. In this case, I've just used L2. And somehow this norm, which could be represented as the inner product of this data matrix, has to represent a physical quantity in the flow field. And so oftentimes I should weight that inner product accordingly. So that's an advanced topic, but one you might hear about a little bit later in the session. But it's an awfully important one, so I wanted to make sure to mention it. And then finally, extended POD does this same process, but only on the observables. And what's important to note about the extended POD is that it doesn't completely span the possible flow states, right? I might miss some with the particular observations I'm taking. Okay, well, so what you're going to hear about in this session, so Larry is going to tell you a lot about POD. It's a really wonderful technique. It's been used extensively, but there are a couple of sort of issues with it. One is that the dynamical systems, the reduced order models, are not necessarily very accurate that you get from POD. And so another theme that Dirk is going to tell you about is how to get better models using a process called balanced truncation or balanced POD. And another important topic is that POD defines things solely at least in this version of POD, it defines things slowly by their spatial structure. And when you're dealing with things like advecting modes, PODs would always have to come out as a pair of modes to represent a traveling wave or an advecting flow structure. And it's nice to get that sort of more automatically. And there are techniques like DMD, Koopman, and spectral POD that give those things to you. I was going to do an example of spectral POD. Here's a beautiful movie that you can appreciate while I take questions. But let me just say in closing that there are a wide variety of useful flow decompositions. I hope to give a basis here by which the talks later in this session can follow on to describe them. There are many connections between these modes, some of which we're only sort of discovering now. So I wasn't able to really fully capture all these different connections between the modes. Maybe some of the speakers a little bit later will do that. But I think for now I'll just put up the pretty picture and take questions if you have them.